The moment everything bent backwards. It started on a Wednesday night, long after the cafeteria had closed. Elena's team had rebuilt a delayed choice interferometer, Wheeler's dare made real with fast modulators and patient grad students. The path length was locked. The detectors were calibrated. Off to the side sat the key, an electro-optic modulator that would, on a randomly chosen whim late in the run, either open the witch path door or close it to let interference through. Their rule was simple: detect the photon first, then flip the modulator. The pattern, by common sense, should be immune. It was. Stakes first because you should feel them. If outcomes depend on later choices, then the neat order we live by, cause then effect, starts to feel negotiable. You can still make breakfast and catch the train, but in the basement of the universe, the rails don't run one way. And if the rails don't run one way, what exactly are we choosing when we choose? Now the action. Wheeler's delayed choice thought experiment was a dare to the cosmos. Take a single photon into a Mach Zander interferometer. If you keep both arms and recombine them, you get interference. The photon behaves like a wave. If you sneak in a device that marks which arm it took, the interference vanishes. The photon behaves like a particle. Wheeler's twist was to decide the setup after the photon had already entered. Dare the world to commit to wave or particle before you ask the question. Technicians a generation later turned the dare into hardware. With fast random number generators and modulators switching in nanoseconds, they chose the measurement late. Even later, some groups sent an entangled partner down a longer path, so the choice basis on that partner happened after the signal photon hit a detector, and they sorted the data in coincidence afterward. In Elena's lab, the late wasn't theatrical, it was engineered. Detection events were time-stamped. A separate controller driven by a random bit toggled the modulator after those stamps. Then they binned the counts. A wave context yielded fringes, a particle context gave a flat distribution. The unsettling part: the wave versus particle look seemed to depend on a choice made after the photon hit a detector. Colleagues joked, the photon knew. Elena waved that off. It didn't know anything. Our story about time did. Here's what actually happened, stripped of slogans. The apparatus produced entangled correlations between the traveling photon and an ancilla that carried the late choice. No signal ran backwards, no message to the past. The correlations were revealed only when you sorted detections by the delayed settings, a pattern in the joint data, not a causal rewrite of isolated events. That's the technical truth. But it doesn't rescue naive causality, because the only way to make sense of the joint pattern is to give up a simple, forward-only narrative for individual outcomes. You can keep no signaling. You can't keep the idea that each detection had a context-free, pre-written character independent of the measurement you later pair it with. Meanwhile, something else was happening on the whiteboard. One student drew the timelines and realized there wasn't a single, clean time order shared by all parts of the setup. Detector clicks, controller toggles, coincidence sorting, their earlier and later belonged to different reference frames within the apparatus logic. That was the moment everything changed for the team. They stopped asking whether the photon switched its mind and started asking what counts as a cause when results live in correlations. Impact because the ripples spread far. Framing it as the photon knew invites a trap. You picture little billiard balls with tiny diaries. The better framing is blunt. You don't get to attribute definite properties to the system independent of the measurement context, including context set by later processing. That's not a press release punchline. It's a working constraint. It kills the kind of causality that assumes a single, global order of explanation for every event. It preserves the causality that matters for signals and control. You still can't send a message to your past self, but it asks you to accept that explanation itself is conditional. Here's a micro story that stuck. Around 2 a.m., a postdoc named Fayez noticed a tiny drift in the timing electronics. Not enough to fake a retro flip, but enough to nag him. He pulled the box, resoldered a joint, and tightened the window that defined after. The flip stayed. He swore, then laughed, then wrote in the log, Past remains susceptible to future definitions. The words were wrong in a strict sense. Definitions don't reach back, but the emotion, dead on. When your final choice determines how you slice the data, it feels like you're tugging on earlier moments. What nobody knew at the time was how central this feeling would become across the field. As teams refined Wheeler's ideas into quantum erasers and entangled histories, they found new ways to showcase that tug without granting it the power to signal. And as theorists built process-level descriptions, where you don't assume a fixed order in the first place, that tug stopped being a glitch and started looking like a feature. To understand why any of this holds force, why we're not just playing with language, we have to go back to the rulebook Bell made testable. He took the quiet assumptions behind the photon new and the world is sane and put them on the stand. Local realism wasn't a slogan. It was a pair of promises. Properties exist before you look, and nothing you do here affects what happens there faster than light. Those promises felt obvious. They didn't survive contact with experiments. Bell's shot at local realism. The Wednesday night feeling in Elena's lab of explanation slipping didn't start there. It traces to a quiet office in 1964, where John Bell sat with pencil and paper and asked a blunt question. Can a universe with local causes and pre-existing properties reproduce quantum predictions? Two pillars framed that question. Realism. Measurement outcomes reflect definite properties that exist before you look. Locality. What you choose or do here can't instantly influence what happens far away. Those pillars felt like common sense. Bell's move was to stop debating them and make them testable. To see why that mattered, we need the setup. Einstein, Podolsky, and Rosen had argued in 1935 that quantum mechanics must be incomplete because you could predict a distant outcome by measuring a partner here. To Einstein, that meant there were hidden variables, unseen details, that fixed results locally, no spooky action required. Bell took that hope seriously and did the math. He derived an inequality, a bound on how strongly distant outcomes could correlate if hidden variables determined them, and if influences respected light speed limits. Quantum theory predicted correlations that could exceed that bound. Stakes before we roll film. If experiments violate Bell's inequality under clean conditions, then any worldview that keeps both locality and realism is out. You can try to dodge with loopholes. Maybe detectors miss a tricky subset, maybe settings aren't free enough, maybe a subliminal whisper leaks through wiring. But each dodge is a bill to pay. Close the loopholes and you're asking the universe directly. Action spread across decades. Early tests in the 1970s and 1980s hinted at violations but left room for doubt. Low detector efficiencies, slow setting switches, short distances. Step by step, labs tightened the screws. Polarization entanglement got cleaner. Electro-optic modulators flipped settings in nanoseconds. Stations moved kilometers apart. By the mid-2010s, multiple groups reported loophole-free violations. In 2015, a team in Delft entangled solid-state spins and swapped entanglement across 1.3 kilometers, spacing events so that any influence would have had to outrun light. Also in 2015, photonics teams in Boulder, NIST, and Vienna used superconducting nanowire detectors and fast random number generators with high detection efficiencies to close fair sampling arguments under space-like separation. NIST's violation cleared the classical bound by double-digit sigma after conservative bias accounting. When the statistics landed, the quantum predictions held, and local realism did not. Meanwhile, something else sharpened: definitions. Bell's local causality isn't just no faster than light messages. It's a precise constraint on joint probabilities. Once you condition on all causes in the past light cone, distant outcomes shouldn't share unexplained correlations. Realism, in this context, means that outcomes are functions of underlying variables that don't depend on which other measurements you perform. Add measurement independence, the assumption that your choice of settings is statistically uncorrelated with those hidden variables. Taken together, Those assumptions define the inequality's limit. Break the limit, and at least one of them must go. Human moments kept the math honest. In one seminar, a young researcher proposed saving realism by letting the hidden variables depend on the measurement settings. A senior colleague asked, "So the settings we choose are already encoded in the variables we're testing?" The room went quiet. You can take that path, superdeterminism, but the universe you get is pre-wired so tightly that free choice becomes theater. Not impossible, just costly. Impact landed with engineering receipts. Loophole-free tests counted every trial, pre-registered analyses, audited timing, and bounded any predictability in random sources. Some used cosmic photons from distant quasars to choose settings, pushing any hypothetical conspiracy back billions of years. Others crowdsourced bits from human clicks to diversify entropy sources. The Big Bell test, 2016, enlisted more than 100,000 participants worldwide in a one-day push to generate setting bits for multiple labs. Even after accounting for small biases, the chance that a local realist model faked the data dropped to vanishing levels. The verdict was signals outrun light. It was you can't keep locality and context-free realism together. Here's the twist that loops back to Elena's night. Bell doesn't force you to accept backward messages or instant telepathy. He forces you to abandon at least one comfortable idea. Many physicists keep operational no signaling, no messages faster than light, and drop the notion that outcomes have pre-existing, context-independent values. Others keep realism but accept non-local explanations, like pilot wave theories with influences that aren't confined by light cones in the underlying picture. Either way, the single, global script of causes gets shredded. A micro-story fixed the feeling. During a late shift, a student plotted correlation curves live as settings flipped. Each new point nudged the Bell parameter past the classical bound. She stared, then whispered, "So the world really does this." Not rhetoric counts on a screen, latencies audited, space-time diagrams taped to the rack. What nobody knew at the time was how the language would change once those diagrams became standard. Locality loophole stopped being a press release phrase and became cable lengths, fiber delays, and clock sync budgets. Freedom of choice became entropy rates and device unpredictability bounds. The romance faded, the constraints hardened. In the aftermath, Bell's theorem became the field's spine. It disciplined stories about delayed choice and quantum erasers. If a late slice seems to sculpt earlier outcomes, check whether you're smuggling realism back in. Pretending detections carry meanings independent of the joint context. Bell showed where common sense breaks. The next wave would test a deeper habit, that there even is a single before and after to hang explanations on. The loopholes slammed shut. While the theory tightened the screws, the defense had three places left to hide: bad detectors, leaky locality, and the uneasy suspicion that the random choices weren't truly free. Stakes were simple. Leave anyone open and a clever local realist can wriggle through. Close all three at once and you're not arguing with metaphors anymore. You're asking nature point blank. No excuses, Elena told the team. Just counts and cones. Action as it moved from whiteboards to racks. In Delft, a team used nitrogen vacancy centers in diamond, solid-state electron spins that could be entangled and then separated by about 1.3 kilometers. They performed entanglement swapping and chose settings fast, so that each side's measurement and choice were space-like separated. The runs were few but clean. Every trial counted, no fair sampling assumption, and a Bell parameter that cleared the classical limit with room to spare. Meanwhile, photonics labs in Boulder and Vienna took a different route. They built bright polarization entangled sources and paired them with superconducting nanowire single photon detectors, whose efficiencies finally crossed the painful threshold where maybe you just missed the unfriendly events stop being plausible, enabling statistically strong violations, e.g., multi-sigma, without fair sampling assumptions. Electro-optic modulators flipped measurement bases in nanoseconds. Random number generators spit out bits at high rates with bounded predictability. Stations were separated by hundreds of meters to kilometers, cable delays measured, fiber length stabilized, and every click time stamped to the nanosecond. They didn't just claim space-like separation, they drew the light cones and published the latency tables. Stakes sharpened around randomness. Freedom of choice isn't a mood, it's min entropy per bit and timing budgets. Some teams sourced randomness from fast physical devices, audited for bias, and folded worst-case predictability into their hypothesis tests. Others pushed further. In one series, cosmic photons from distant quasars set the switches, so any hidden coordination would have needed roots billions of years old. In another, the Big Bell test, 2016, enlisted more than 100,000 people worldwide in a one-day push to generate setting bits for multiple labs, an explicit attempt to address freedom of choice, concerns by diversifying entropy sources. Human moments kept it from becoming a cartoon of perfection. In one late run, a graduate student, Anna, found a 3-meter mismatch in fiber lengths between stations. She caught it at dawn by watching phase drift when the building HVAC cycled. The fix was a coil of fiber on foam, labeled thermal, do not touch. That coil turned a fuzzy spacetime diagram into a clean one. Days later, the violation reappeared exactly where the inequality said it shouldn't. Meanwhile, something else was happening in the statistics. The field adopted analysis discipline that would have made a skeptic smile. No cherry picking. Every attempt counted, successes and misses. Pre-registered analysis pipelines. Explicit p-value calculations that included worst-case biases in the random sources. Adversarial tests where timing skew was deliberately injected to confirm the violation vanished on cue. When the numbers landed, 2015, and after, the chance that a local realist model produced the data fell to vanishing levels. Clarify what actually closed. The detection loophole, high-efficiency detectors and careful accounting so you don't assume the sample you measured represents the whole. The locality loophole, space-like separation between each side's setting choice and the other side's outcome, with device latencies verified, so no subliminal nudge can sneak through. Freedom of choice, demonstrated independence between settings and any variables that might influence the outcomes, bounded by entropy estimates or driven by sources outside the lab's past light cone. None of these moves smuggle superluminal messages into the story. They just corner local realism until it runs out of room. Micro-story from a control rack. Fayez noticed a weak correlation between an RNG's temperature and its output bias, still within spec, but enough to make him sweat. His hand shook a little when he pulled the module. Missing a bias like that is how careers get dented. They halted, replaced a jammed fan, recharacterized min entropy, and reran with the bias folded into the hypothesis test. The violation shrank a hair and got more convincing. In the log, he wrote, less pretty, more true. Impact wasn't a single trumpet blast. It was a stack of receipts. Delft's solid-state test shut the door on detection and locality with matter qubits. Boulder, Vienna, and others did the same with photons, high rates, and unforgiving counting. Cosmic source test shoved any hypothetical conspiracy into the deep past. The message was boring in the best way. Under conditions designed by skeptics, quantum correlations violate Bell's inequality. If you insist on saving both locality and context-free realism, you're left paying with superdeterminism, a universe where your setting choices are baked into the same variables that decide the outcomes. Not logically impossible, just a bill most aren't willing to pay. Meanwhile, the culture shifted. Papers started printing spacetime diagrams alongside correlation plots. Latency budgets sat next to visibilities. Randomness extractors got footnotes with min entropy bounds. Labs ran blind analyses, separating exploration from confirmation. What used to be a headline, loophole-free, became a checklist. Distances, delays, efficiencies, entropy rates, jitter tables. Here's the moment that fed back into Elena's lab. With locality's explanatory shelter gone, the team stopped reaching for hidden signals and started watching how context defines meaning. No faster than light messages. No retro phone calls. Just a hard limit. You can't tell a single, global, context-free story about outcomes. That limit didn't just kill a worldview. It shaped the next question. If space can't salvage a classical script, maybe time won't either.